Welcome. In this video I'm going to show you how you can obtain the number of bins using R. I'm using Jupyter Notebook, but this should also work in, for example, or at least the R code should also work in, for example, RStudio. I'm running version 4.3 of R, and I only have the basic packages that come usually with R installed. So the number of bins is actually a little bit tricky. Some will use some rules of thumb, others will have some formula. So there's not one method that can do this. To show you how it can be done, I'll load in some example data from the General Social Survey of 2012, adjusted for these examples. I don't need actually all their data, I only need one numeric field, so I'm going to be using the H field. However, there is a category 89 or older, so I'm just going to using the replace function, simply going to make that into 90. Remove any missing values and just make sure it's a number. So starting off with selecting the age field, removing the missing values, replacing the 89 or older with 90, and then just make sure it's a number. And then I have a vector with the scale numbers. I have a separate video on how you can simply use my tab nbins function from my own library, but in this video I'm going to show you how it can be done without libraries. So first of all, we have of course these. You can simply these rules of thumb. If you want to use those, you can simply make a small if statement, and that's about it. I'm going to be focusing on the ones that use a formula. So we have the square root choice, for example, the Sturgis. This actually, by the way, means to floor, so ceiling, so it means to round up these kind of brackets. There's a quartic root, which is 2.5 times the quarter root of n, where n is the sample size. So as you can see, these either use some root function or a log function. All of that is available with R, so it's a matter of simply filling out the formula. Most of them do require the sample size, which we can simply get by using the length, and then you can just plug in the formulas using the ceiling function to round up. So these are actually fairly straightforward to obtain just by plugging in the formulas. And as you can see, they do vary quite a bit. Slightly more complex is a method by Dwayne. He says 1 plus log 2 of n plus the log 2 of 1 plus, and then this is where it gets tricky. This is the skewness, and this is then the variation of the skewness. That is calculated using this formula. And the skewness itself is then calculated using this formula. There is actually another way of calculating it as well, but I'll show you that one later on. R actually has an absolute function, a sum function, and an average function. There is no standard deviation function. Well, there is one, but it returns the sample standard deviation, not the population version. So the difference is that instead of dividing by n minus 1, we should actually divide by n. We can do that by simply multiplying the sample version by this, and that gives us then the population version. So looks a bit daunting in the beginning, but actually it's not that complicated. Alright, so here is all of that. So the standard deviation of the population is the square root of the n minus 1 divided by 1, that's this one, times the standard deviation of the sample, which actually is that one. The skewness is, as you can see, was the sum of the scores minus the average. So the scores minus the average, and then to the power of 3, actually I'm using this formula over here, so to the third power, divided by, and then what I'm doing here is I'm simply taking the sample size n minus 1 actually, and then to the power of 3 of the standard deviation of the the population standard deviation to the power of 3. Then this one, that's going to be simply the square root of 6 times n minus 2. So the 6 times n minus 2 and n plus 1 times n plus 3. So n plus 1, n plus 3. And then we have finally everything to calculate the number of bins according to Dwayne. Some actually have formulas where it's not based on the sample size. They don't give you immediately actually the sample size, but they give you how wide every bin should be. So you can use the maximum minus the minimum divided by the width, and then you actually get your number of bins. So Scott and Freeman Diaconis, they both have formulas for this. That are fairly straightforward. They do require, this one does require the interquartile range. There are tons of different ways of actually calculating the quartiles, but I'll keep it short and just simply use the IQR function that R has in its stats library. And it's just a matter of filling out the formula. So these are not too complicated. There are also some algorithms that can be used. I won't go into all the details of these. I've programmed them in, or at least I try to. This is by Shimasaka and Shinomoto. Hopefully I pronounced that correct. This was their version. And here you can see it in action. Stone actually had a similar ID, but they use minimizing A rather than maximizing. So here is their version. And Knuth had just another maximizing ID, tries to maximize. So these go over all possible options and then try to find the maximum or minimum result. Alright, I hope this video was helpful and thank you for watching.